We will now study measures on rings. Recall X is a non-empty set and you have R is a collection of subsets which is closed. So this is a ring, which means EF belong to R implies E union F and E minus F belong to R. Then we also saw what is a sigma ring, what's an algebra and such things. So now we want to define a measure on a ring. So let X is a set and R is a ring of subsets. So definition: a measure mu on a ring R is an extended real valued function defined on R such that 1. Mu e is greater or equal to 0 for every e in R. 2. Mu phi is equal to 0. And 3, this is the most important property, this is called countable additivity. So ei I equals 1 to infinity is a countable collection of sets in R which are mutually disjoint. That means ei intersection ej is empty if I is not equal to j. If E equal to union I equal to 1 to infinity ei belongs to R, because this R is a ring, it is not closed under countable unions in general. So we have to make this assumption. If you are talking about sigma ring, which is the advantage, we don't have to make this extra statement. Then mu of E equals sigma I equals 1 to infinity mu of ei. So in checking when something is a measure, this is the main thing which we have to check. Other properties will be obvious. And this is the main advantage of Lebesgue's theory. Okay, so before Lebesgue, people did try to do things like this, and they always stuck with finite additivity. That means if you have a finite collection of disjoint sets, then the measure of the union is the sum of the measures. That is obvious because we have areas or lengths. If you have disjoint sets and you put their union, then you can define the length or area to be the sum of the individual values. Okay. But Lebesgue found that putting this condition of countable additivity, which was not obvious intuitively, helped to make a very rich theory of integration and measure, and that is the advantage of these things. So we have, as usual, several remarks based on this definition. First of all, it is possible that there exists E in R such that mu of E is infinite, because it's an extended real valued function. So there can be sets whose measure are infinite. Secondly, 2, if there exists an E in R such that mu E is finite, in fact that is will always be the case, otherwise it's not an interesting measure, then 2 follows from 3. Because you can write E equals E union empty set, union empty set, union empty set, and so on. And therefore, if you now write the countable additivity, you get mu e equals mu e plus mu phi plus mu phi plus mu phi, etc. And since mu e is finite, I can cancel it on both sides, and therefore I'll get mu phi equal to 0. This again I want to emphasize that when you should be able to cancel only when the quantities are finite in an equation if you want to do it. If something is infinite, then cancelling on both sides is absurd. Okay. Then 3, mu is finitely additive. So if ei I equal to 1 to n mutually disjoint, then you can write E equals, the union is obviously in the ring because it's a finite union. So E1 union etc. En union phi etc. And therefore you get that. So that will imply that mu E is equal to sigma I equals 1 to n mu of Ei. So now, okay, so now it's time to give some examples. So example 1. So X, any non-empty set, okay, and R is the power set of X, all subsets. So you then define mu of E as the following fact. This will be 0 if E is empty. Number of elements in E if E is non-empty and finite, and plus infinity otherwise. So if you have infinite number of elements in E, then you put mu E equals infinity. So we have to check. So the first property, it's non-negative and it is 0 for the empty set. So we only have to check countable additivity. So Ei I equals 1 to infinity, mutually disjoint. Of course, in this case we are in the power set, so E is equal to union Ei. So first case, E is finite. This implies Ei are empty for all but a finite number, and those non-empty sets are also finite. In this case, the additivity is obvious because the empty sets will all contribute 0, and you know the number of elements in a if you put the union of a finite number of finite sets, then the number of elements in the union is the sum of the number of elements in the individual sets, and that gives you precisely the additivity property. So if E is infinite, then you may either have there exists a Ei which is infinite, or there exists infinitely many non-empty finite Ei. In either case, if you take the sum on one side and the other, both sides will be infinity, and therefore the countable additivity is established. Okay, so second example, so this is called the counting measure. Okay, so mu is called the counting measure because it counts the number of elements in the set. The second is again X is any non-empty set, and you have R equals P of X, and then you have mu of E equal to, and let X naught belong to E, belong to X. Mu of E is equal to 1 if x naught belongs to E, and 0 if x naught does not belong to E. Okay, so now again this is non-negative. Mu of the empty set is obviously 0. So we have to check countability. So if EI mutually disjoint, and E equals union I equals 1 to infinity EI. So if x naught does not belong to E, this implies x naught does not belong to EI for all I. So both sides of the equation, so we want to know if mu E is equal to sigma I equals 1 to infinity mu of EI. So in both sides of the equation everything is 0, and so it's obviously true. If x naught belongs to E, this implies there exists a single I naught such that x naught belongs to EI naught, and x naught does not belong to EI for all I naught equal to I naught, because the sets are mutually disjoint. So now then this will be 1 on this side, and there will be exactly one term which is 1, and all the rest will be 0. Okay. So this is the second example. The third example is something like the first example again. So X is again any non-empty set, and R equals P of X. Okay, and then F is from X to R, non-negative function. Okay, so then okay, so let us, no, R is not the power set, so let us not write power set here. R equals ring of finite sets. We have already seen this. So this is a ring because union of finite sets is finite and difference of finite sets is again finite. So this is a ring, and therefore, and then you define mu of any finite set x1 xn is equal to sigma I equals 1 to n f of x, and you can check. So check mu is a measure. One remark I forgot to tell you in the countable additivity here. So when we wrote the countable additivity equation relationship here, the order in which we write the EIs is not important, because you have a series of positive terms, and so since all the now elements are positive, you can write them in any order, the answer will always be the same. Okay, so that is, you don't have to worry about the convergence of the series. Okay, so we have these things. So the most important and interesting example is the Lebesgue measure, which we will construct in detail a little later on. So now we will just prove some properties of measures. So proposition 1. So X non-empty, R a ring on X, mu a measure on R. Then 1. Mu is monotone. That means E contained in F implies mu E is less than or equal to mu F. And 2, mu is subtractive. So if E is contained in F and mu E is finite, then mu of F minus E equals mu F minus mu. Okay, so proof is just one line. Okay, so E is contained in F, and therefore we can write F is equal to F minus E union E, and this is a disjoint union. And then by finite additivity, you have mu F is equal to mu of F minus E plus mu of E. So this is finite additivity. So this immediately tells you mu e is less than or equal to mu f, because everything is non-negative, and if mu e is finite, I can subtract both sides of the equation, mu e from both sides of the equation, and therefore I get the result. Okay, so next proposition, this is called subadditivity. So again, X non-empty set, R a ring, mu a measure, and EI in R, EI in R, okay, and you have that, so this is a finite or infinite sequence, okay, and E in R such that you have E is contained in union EI. I won't write I equals what, I'll just write union over I, because it could be finite or infinite. Then mu E is less than or equal to sigma I equals 1 to infinity mu of EI. We are not talking about disjoint, nothing here, arbitrary sets in R, and E is any subset. In particular, if the union itself is in R, then if E is the union, and then you have this inequality always true, irrespective of the fact whether they are disjoint or not. If they are disjoint, then it's equal. If they are not disjoint, it's less than or equal to. So proof. So you set Fi equals E intersection EI, and you define G1 equals F1, and then Gi equals Fi minus union J equals 1 to I minus 1 Fj. So I am breaking it up as a, so then you have that Fi is contained in EI, and then Gi is contained in Fi, okay, and Gi's are disjoint because I have taken away all the previous elements, so it's always these are disjoint. So by monotonicity and countable additivity, this implies that mu of E. Okay, so what about union Gi is the same as union Fi, and that's same as E, okay. So mu of E by countable additivity is sigma mu of Gi. Now Gi is contained in Fi, so by monotonicity this is less than or equal to sigma mu of Fi, and Fi is contained in EI, so this is less than or equal to sigma over I mu of E. So X non-empty, R ring, mu measure on R, EI finite or infinite sequence of sets in R, mutually disjoint. E is in R such that union I EI is contained in E. Then sigma mu of EI is less than or equal to mu of E. So this is more or less obvious. So proof: for every positive integer n, union I equals 1 to n EI is contained in E. Okay, and therefore you have sigma by the finite additivity, sigma mu of ei, I equals 1 to n is thus equal to mu e. Okay, and then from this you deduce the result immediately. If n is, if the set is, collection is infinite, you let n tend to infinity, otherwise you stop at whatever n you have. Okay, so this is so now we have a very important proposition, very important property of measures. So this is called continuity from below. It helps us to compute things. So X non-empty, R a ring, mu measure. Okay, now EI is an increasing sequence of sets in R, and union EI, I equals 1 to infinity equals E also belongs to R. Again, if you are in a sigma ring, I don't have to make this extra statement, that's obviously true, otherwise. Then mu of E is the limit as n tends to infinity mu of En. So if you have an increasing sequence of sets and you take the union, then the measure of the union is nothing but the limit of the measures of these sets. So proof, we set E naught as the empty set, and then you can write mu of EI, E so this is nothing but mu of union EI, I equals 1 to infinity. Now this union, I am going to break it up as disjoint sets. So you have E naught, so first one E1, then I will take just this portion here, then I will take just this portion here, and then I will take just this portion here, so that I can write this as a disjoint union. So this is equal to mu of union I equals 1 to infinity of EI minus EI minus 1. And since these are all disjoint, this is equal to sigma of mu of EI minus EI minus 1. But that is equal to limit as n tends to infinity sigma I equals 1 to n mu of EI minus EI minus 1, but by finite additivity this is equal to limit as n tends to infinity sigma mu of union I equals 1 to n EI minus EI minus 1, but this is nothing but En, and therefore the theorem is proved. Okay. So next proposition is just the same previous proposition in a slightly disguised fashion. So proposition 5. So this is continuity from above. So X non-empty, R ring, mu measure on R, and then you have EI I equals 1 to infinity decreasing sets in R, and you have intersection I equals 1 to infinity EI is also in R. So that's also a hypothesis. If mu of EM is finite for some m, then mu of intersection EI I equals 1 to infinity equals limit n tending to infinity mu of En. So in the case of intersections, you have to assume the fact that one of the sets at least is a finite measure, which means that all the rest which are above, beyond that are also finite measure, because you have a decreasing sequence. So proof, We have mu of En is less than plus infinity for all n greater or equal to m, because En is decreasing. Okay, so and you have Em minus En, n bigger than or equal to m, is an increasing family, because Ens are decreasing. If you take the complements, they will be increasing, and hence you have. So now you write mu of Em minus mu of intersection I equals 1 to infinity Ei is equal to mu of Em minus mu of intersection I equals m to infinity Ei, because it's a decreasing set, so we are taking intersection, whether, so you can start it from m instead of from 1. Now that is equal to mu of Em minus intersection I equals m to infinity Ei by the subtractive property, because this has finite measure. So when you subtract, so this is nothing but the measure of the difference. So that's equal to, by the De Morgan law or whatever you like, so this is equal to union I equals m to infinity of Em minus Ei. But we just saw that these are all increasing sets, and therefore this is equal to limit as n tends to infinity mu of Em minus En. And mu of Em minus En is mu Em minus mu En. Mu Em is a constant, so this is equal to mu Em minus limit n tending to infinity mu of En. And that's exactly, now you can, because mu M is finite, I can cancel it on both sides, and therefore I get the result which I need. Okay, now example prop 5 not true if finiteness assumption is lost. So for instance, you take natural numbers n and counting measure, and you take En to be set of all m such that m is bigger than or equal to n. So then EMs are decreasing, and mu of Em is plus infinity because it's an infinite set all the time for all m, for all, so En, sorry, okay, and so ENs are decreasing, mu of En is for all n, and you have that intersection n equals 1 to infinity is empty. So the measure of the intersection is 0, but the limit of this is still always infinity. So the equation, the result is not true, and you have here. Okay. Now we have one more definition. Okay. So X non-empty, R a ring, and mu a measure. Okay. Then we say that mu is finite if mu E is finite for every E in R. So it's called a finite measure. Sometimes it's also called a probability measure. We'll see that later. But it's, let us say it's just called a finite measure. Mu is sigma finite. So again, you see, I'm bringing in this sigma here. If E can be written as union EI, I equals 1 to infinity, mu EI finite, okay, and for every E in R. Every set E can be written as a countable union of sets of finite measures. Then you call it a sigma finite measure. So if you take Dirac measure, I don't know if I mentioned the name. Yeah, this measure is called the Dirac measure. Concentrated at x naught. Okay, this is called the Dirac measure, concentrated at x naught, and that is of course a finite measure. So Dirac measure is a finite measure. Counting measure on n is sigma finite, because if you write take any infinite collection of natural numbers, you can write it as a disjoint union of singletons, and each singleton has measure 1, so it is finite, and therefore you can write it as a union of a sum or a union of sets of finite measure, countable union of sets of finite measure, and therefore this becomes a sigma finite measure. So now we conclude with a very, very useful result which we will use later, but it's a very pretty result. So proposition, this is called the Borel-Cantelli lemma. Very nice result. So x non-empty, you have S sigma algebra. It's not very important, but I'm just stating it because that's how we will use it all the time, and then mu a measure. Okay, now I equals 1 to infinity, sequence of sets in S such that sigma mu of I equals 1 to infinity is finite. So the series consisting of the measured values is a convergent series. Then, except for a set of measure 0, every point x in X belongs to infinitely to at most finitely many EI. So that means what? So you take E is set of all x in X, so set x belongs to infinitely many EI. Then the lemma says that mu of E is 0. That's what we must try to prove. Okay, so this is a very, very beautiful result and very useful in many situations. So proof. So what is E? E is x belongs to infinitely many EI. That means for every n, so x is in E, if and only if for every n there exists a I bigger than n such that x belongs to EI. That's what we mean by saying x belongs to infinitely many EIs. Okay, so that means E can be written as sigma, this is a very nice, n equals 1 to infinity, union I equals n to infinity EI. Okay, so once you have this, then for every positive integer n, you have mu E is less than or equal to mu of union I equals n to n infinity ei, which we know by subadditivity is less than or equal to sigma I equals n to infinity mu of ei. But this is a tail of a convergent series. Therefore, for every epsilon positive, there exists n such that sigma I equals n to infinity mu of ei is less than epsilon. So this means mu e is less than or equal to epsilon for every epsilon positive. That means mu e equal to 0. So this means mu e equal to 0. So this is the Borel cantilever. So our next objective is to, given a measure on a ring, we would like to see if we can extend it to something. So for instance, given a ring, I can think of the smallest sigma ring containing this ring. Okay, we have already seen such things. Given any arbitrary collection of sets, what is the smallest ring containing that collection, or what is the smallest sigma ring containing that collection. So if I am given a measure on a ring, I would like to extend it to the smallest sigma ring containing it, and so on. So such extensions we would like to study, and we will do it next time.